This is the lecture for section 3B, putting numbers in perspective. One way that we will see numbers written is in scientific notation. This is used when a number is very, very large or very, very small. Scientific notation is going to be in a format where the number that you start with is between 1 and 10, and then it's going to be times 10 to a power. The power will be positive if the number is greater than 1, and the power will be negative if the number is less than 1. And then the number that is in the power tells me how many times I moved the decimal point to get it to the spot. So, for example, 6,700,000,000 in scientific notation is 6.7 times 10 to the ninth power, because this is clearly a number larger than 1. And the decimal to go from 6.7 to the end of the number, so starting here, going to the end, that's 9 places away. This number down here is 2.0 times 10 to the negative 15. And yes, you do have to put a 0 there, even if there are no numbers after it. And it's smaller than 1. And we have moved the decimal 15 places to get it from there to here. We are going to write some numbers as ordinary numbers and then write ordinary numbers in scientific notation. So the first one here says write 3.4 times 10 to the fourth as an ordinary number. Now, the way that you do this, to the fourth, positive means I'm going to make my number larger. So I'm going to move the decimal to the right 4 places. 1, 2, 3, 4. And I'm going to fill in with zeros where there are empty. So 34,000 is the same as 3.4 times 10 to the fourth. 1.23 times 10 to the negative 6 wants us to make the number smaller than 1. So we have to then move this decimal back 6 places. 3, 4, 5, 6. And fill in with zeros. So 1, 2, 3, 4, 5 zeros. 1, 2, 3. And you can see 1, 2, 3, 4, 5. That's where my zeros got filled in. Now, if I have the number written as normal and we want to turn it into scientific notation, we're going to count how many places we have to move it. And we're going to move it until we get to the first number larger than 0. So I moved it 1, 2, 3, 4, 5 places. So 3.04 times 10. And this is negative 5 because the number is smaller than 1 to start with. And then this last one here, we want to do 247,986. We want to write this in scientific notation. So currently the decimal is at the end here. If it's not written, it's at the end. And we're going to go here 1, 2, 3, 4, 5 places. So the decimal now is 2.47986. And I need to use all the numbers that are there times 10 to the 5th power, because we counted 1, 2, 3, 4, 5 places. The following is a table for energy that is used by all sorts of different things. So, eating a candy bar, running, up to how much energy is consumed in the world or the sun. We're going to use these values to compare and figure out how much larger one is from the other. Compare the US population to the world population and US energy consumption to the world energy consumption. What does this then tell you about energy usage by Americans? So, what we're going to do is we're going to use what we did in the last section of finding percentages to figure out how these two values compare. So, the first they want us to do is compare US population to the world population. So our US population was 300 million, or 3 times 10 to the 8th, and the world population is 8 billion, or 8 times 10 to the ninth. So we take the US population on top divided by the world population here. That ends up just giving us 3/8 times 10 to the negative 1, or 0.0375. If I multiply that by 100, I get 3.75%. So the US population makes up 3.75% of the entire world's population. So what we just found on the last side was about the US population is about 4% of the world's population. But if we look back at the tables for energy consumption, US energy was 1.0 times 10 to the 20th, and world energy was 6.3 times 10 to the 20th power. And you can, again, go to any scientific calculator, type this number divided by this number, and we're going to get a decimal. And that decimal is 0.159, so rounded. That can round to 0.16, which if I turn that into a percent is 16%. So that's where the rest of this comes from. The United States uses about 16% of the world's energy. And if you compare that to their population, that is 4 times as much as their population. I would like you to try to compare the energy released by burning 1 kilogram of coal to the energy released by burning 1 liter of oil. And if you go back 3 slides, you can go back to that table, grab those numbers, and if you want to, you can type your comment on the slide for the answer that you got, or you can comment it with a voice message. Another way that we can put numbers in perspective is when you look at something like a scale on a map. So, this map here has this grid thing on the bottom here where it says this represents 1 kilometer, this represents 2 kilometers, 3 kilometers, so on and so forth. And the distance here is actually a centimeter. So if you took a ruler and lined it up here, this would be 1 centimeter represents 1 kilometer. And then 2 centimeters is 2 kilometers. So what that means is 1 centimeter is equal to 1 kilometer, and that scale ratio 1 to 100,000. A kilometer is 100,000 centimeters. So this is a very small scale to represent the actual distance between places. In this map, we see that the scale is 1 inch represents 16 miles. So if we were to roughly draw a straight line here between Sheffield and Norwich, it says that would measure about 9.75 inches. Could we then determine how far these actual cities are apart from each other? Well, sure. So we are going to use the inch measurement compared to the mile measurement. Our scale says that 1 inch represents 16 miles. What we have is 9.75 inches, and we want to find the actual distance in miles. So we don't know this one. So I'm going to set up a proportion here, and then once I have a proportion, we can solve this by cross multiplying and dividing. So if I multiply here, 1 times x is just x, and 16 times 9.75 is 157 miles. So on the scale map here, they're 9.75 inches apart. In reality, they're 157 miles apart. So, how large is $1 billion? We talk about that. You may see the number a billion, but how big is it? So, one way to think about that is to ask yourself, how many people could you employ if you had $1 billion? So, let's say your employees were going to receive the salary of $100,000, and that it costs a business an additional $100,000 per year for overhead in each employee. So, for every employee you hire, you are going to have $100,000 that goes to their salary, and then $100,000 that goes for their office space, their health insurance, their retirement, and all things like that. So, what they're saying here is the total cost for any employee would be $200,000. So, if we wanted to figure out how many we could hire, we're going to see that on the next slide. So, we would take that $1 billion that we have total divided by $200,000 per employee. Now, we can rewrite these numbers in scientific notation. 1 billion is a 1 with 9 zeros, or 1 times 10 to the ninth. $200,000 is 2 times 10 to the fifth. And then we can go to our calculator and type 10 to the ninth divided by 2 times 10 to the fifth. And you'll get 5 times 10 to the third if your calculator says scientific notation, or it may just spit out 5,000. I'm going to show you on my scientific calculator here on the next slide what that looks like. But for now, this means if I had $1 billion, I would be able to hire 5,000 employees. The one calculator I will use a lot is Desmos. And you can see here, I entered those numbers 10 to the ninth divided by 2 times 10 to the fifth, and I just got 5,000. So feel free, if you do not have a scientific calculator, to go to desmos.com and use that for all of your calculations. Now, we hear these words millions, billions, trillions, and do you really understand how much different they are? How far apart they really are? Well, let's look at it this way. If you earned $1 million a year, how long would it take you to earn $1 billion? Well, to do that, I would just divide a billion divided by a million. Well, a billion is 10 to the ninth. A million is 10 to the sixth. So that leaves 1,000 years. So even if you're earning $1 million a year or $2 million a year or a few million a year, you are not going to become a billionaire in your lifetime. Another way that we can put numbers in perspective is by converting these units. So there were approximately 2.85 million deaths in the United States in the year 2019. We want to figure out how many that is per minute. Now, I could have asked per day, per hour, per second. I could have changed the value, but we're going to do minutes. So 2.85 million. 2.85 million means 2.85 times 10 to the sixth power. And that is per year. So what I need to do now is figure out how many minutes are in a year. And I'm sure you could Google how many minutes are in a year and it's going to tell you. But I'm going to show you here. 1 year is 365 days. And in a day are 24 hours. And an hour is 60 minutes. So if I multiply 365 days in a year, 24 hours in a day, 60 minutes in an hour, I get 525,600 minutes represents a year. And I can now do my division by minutes. 525,600. So again, you could go to Desmos or open any scientific calculator. If you take 2.85 times 10 to the sixth divided by 525,600, you get about you're going to get 5.42 in your calculator. So this means about 5 people die every minute in the year 2019. At the end of 2019, the US gross national debt was about 22.7 trillion. If the population was 330 million, about how much debt is this per person? So let's recap here. Million is going to be 10 to the 6th. Billion is going to be 10 to the 9th. Trillion is 10 to the 12th power. So when you see 22.7 trillion, that's 22.7 times 10 to the 12th. When you see 330 million, that's 330 times 10 to the 6th. So again, grab any scientific calculator. If you do this division, you're going to come out with $68,787.88. And this was back in 2019. So that means for every person that was alive in 2019, this was the amount of debt that they, as an individual, could take up as far as the total US debt. This is actually the last slide for this section, so please go on and watch the lecture for 3C.